All right, so thanks a lot for the invitation to speak here today about validation. So my name is Annika, I work at the German Cancer Research Center. My main focus there is actually validation of AI, and I'm also part of the MONAI working group for reproducibility, evaluation, and benchmarks. So perfect fit for this topic. And the things that I will be presenting are especially things that we have been working on throughout our working group and also part of efforts for the other group members. So I'm very happy to share the results. Mostly from a theoretical point of view, we have already some things integrated in MONAI, and I will let you know what are the things that we plan in the future. So validation is a topic that is close to my heart, but for many people, something that you perhaps in the beginning don't really care about. So if you're developing your models, you probably think of, okay, what network architecture should I use? What are the things that I should do to my model? Should I add attention modules or skip connections or whatever? And validation is something that typically comes a bit short. And today I would like to talk about the issues of doing that and the problems that we have with validation and how we can solve them. So the important thing to notice is that validation actually guides scientific progress. So if we imagine the road that we see here, we can see our algorithms somewhere over here. So we develop an algorithm, see it as a car, for example, driving on that road, and over time, we're going towards a specific direction. So we're optimizing a specific goal. And this could, for example, be translated with a specific metric that we're focusing on. So we're evolving our algorithm, we're making sure we're training it, we're validating it, and then we're going into this direction. The problem is that the optimized goal is not necessarily the same as the real goal, for which we, for example, need an adequate metric. If we have a very simple example here, so we see this reference at the top, so we have these three objects here, and what we want in reality is something like an object level metric. So something that tells us your algorithm only detected 1 out of 3 objects, so it's not great. But what we often do in practice for such detection problems is just using a pixel level metric. So something like a segmentation metric, which will tell us, well, from a pixel point of view, you detected most of the pixels, so you're very good. Meaning that we're optimizing something that is not what we want. And this is what we try to convince people with the working group at MONAI, that we are going towards the real goal. And today I would like to use a specific example related to the topic of which algorithm works best for a specific problem. Because this is basically the ultimate goal that we have, right? We're working on algorithms, we're developing, and we want to make sure basically that we are the best, right? If we are writing a paper, we often see something, yeah, we're outperforming the others on this kind of problem, but then comes the next paper saying that they're outperforming your paper. Basically, we have many, many papers, and it's really hard to distinguish which algorithm is really the best. And to solve this problem, if we look at how this is done for example, new medication or new treatments in the clinic, there are very specific rules for that, right? So if you want to assess if the new medication is better than something old, you do clinical trials. So very straightforward. You have a very strict process here. You have regulations, you have quality control. And the equivalent that we have for AI are challenges. So image analysis competitions in which you compete against each other on the same data set, under the same conditions, for a fair comparison, to really find out, under the same condition, which algorithm is really the best. So you compete against each other, and typically this challenge announces a winner. And this winner often gets high prize monies, which is of course a nice side effect. At least if you're working with Kaggle, for example, you can go up to 1 million euros or dollars. But from a scientific point of view, these algorithms are seen as the new state of the art. If we think of the decathlon, NNUNet definitely changed our whole research structure. So the researcher gets famous, is highly cited. This is the new method we use for this kind of problem. So these challenges have a very important role and are related to benchmarking and also related what we want to show in one eye. So challenges are a very important part of our science. So on the one hand, which is also nice, they often publish data sets. So we can use them for our validation, for benchmarking, etc. And probably you will find a challenge for your needs. You have various fields of application covered, various modalities. So challenges drive the research field. This is, of course, one obvious reason why I'm bringing them up as an example. The other reason is what we are doing when we publish a paper is something like a mini competition, a mini challenge, because we're doing somehow exactly the same. We're comparing our algorithms to other state-of-the-art methods. And ideally, we want to show that we are the best. So you often see these tables and comparison, and this is why I'm bringing up the challenges as an example. They are so important because we're actually doing the same thing all over again in our research. So all of the things that I'm telling you also apply for our research. So given the importance of challenges and benchmarking, a few years ago, we had the question, is the winner really the best? Because challenges are so important and we base our whole research upon these challenges. And I can already tease you, there's a very high discrepancy between the high impact of challenges and missing quality control. And in my talk, I will be talking about different topics related to validation and problems for challenges and also for our algorithms. And I hope that you get some take-home messages from them. So let's start with reporting. Probably the easiest choice here, something that is also not very, seen as a bit boring, for example, for instance, but reporting is something very important. And as you see here from this quote from this paper here, the authors state, and they are correct, that the one practice that can be universally commended is transparent and complete reporting of all facets of a study. It's important for us to know what people did to understand, interpret the results, and also be able to reproduce the results. Because in the end, we would like to use those algorithms, right? So back in the days, we started with thinking about what are the things that should be reported for challenges. And there are some obvious things like how large is the data set, how many people participated, what are the metrics, but also some that may perhaps be not so obvious. For example, participants allowed to use their own data other than the data shared by the organizers? How do you treat missing values, and so on and so forth? So we analyzed more than 500 competitions, and we found that reporting among challenges was quite poor, honestly. So there was a median of 64% of all these parameters reported, and only 6% of these parameters were reported by all challenges. To give a few examples, 85% of challenges didn't give any instructions on whether the training data that was given by the organizers could have been complemented by their own data or publicly available data. And if we think of challenges as a fair comparison, this is definitely not fair if you think of a lab that has just access to more data than a lab that doesn't have this data. Also, in 66% of tasks, there was no description at all how the reference annotation was performed. Again, a very important problem. So to solve this problem, we have sat together with many experts in the field, and we have written a reporting guideline. Also here, we had a look at how clinical trials do that, and there are many, many guidelines out there, but there were at this point not so many for AI. So we worked on a guideline for reporting and also designing challenges. So we collected all these parameters should be reported, and from experience, from having organized a challenge and using these guidelines for writing the paper, it definitely helps you a lot. And so we registered this with the Equator Network that you see here on the right. And I would definitely recommend you checking this out, not only for this challenge guideline, but they now also have a lot of guidelines for reporting AI for different situations and use cases. So this is really helpful for writing your paper because we tend to forget things. And I would like to illustrate this with an example. So a study that we did a few years ago with the question of whether challenge algorithms are reproducible. So imagine the situation, you follow a competition and you would like to use that algorithm that wins the challenge. And perhaps you have faced the situation that you see an algorithm, you think that is really promising, I want to use this for my own research. You try to reproduce it and you just don't get the nice results that they have shown as a winner. So we wanted to look at this a little bit more systematically. So we did a study on a challenge that we have organized by ourselves. So we had access to all the method descriptions of the participants. So this, just to give a little bit of context, this was a challenge for instrument segmentation for different surgery tasks. We had 7 participants, and 5 of them used mask-Gaussian ends, and 2 of them used units. As part of the submission process for the challenge, we required participants to submit a document summarizing their methods, and we said in detail to the point of being reproducible. So we asked them to describe what you see basically on the right. So we specify the things that should be reported. And we used those method descriptions for the basis for reproducing the algorithm. So we didn't look into publicly available implementations. We just wanted to use their descriptions to see what we can do from that. And just to give you some insights from those 7 teams that participated, the descriptions had a median length of 5 pages, maximum length of 10, and minimum length of 2. So I think you can already imagine that there was a high discrepancy in the amount of information provided. So we did a reproducibility study, so we tried to stay as close as possible to the method descriptions. In case there was information missing or there were ambiguities, we first reviewed cited literature, or we reviewed secondary literature that was related to the task or network. And whenever we couldn't do that, we had a look at publicly available implementations of similar approaches. And if we compare the results, so in dark blue, we see the original results versus the re-implementation results in green, we see that there is a large gap between those two. So we definitely were not able to reproduce the good results that they had in the challenge. And if we look at the rankings, so we had 2 rankings back in the days for the challenge, we also see that the rankings changed quite a bit. So we wanted to know, why is this the case? We looked a little bit deeper in the descriptions, and you see a few examples here. So we defined minor deficiencies and major deficiencies. For example, something minor would be the optimizer was not specified, but based on the description of the hyperparameters, it was very plausible that they use SGD. And something major would be that, for example, the model selection process was not specified at all, and we couldn't get any intuition of how they did it. And when we put this together, we came up with different categories. We found that the model selection and data augmentation were the things with the most problems, but also data split was often not specified. Inference, and the worst one for one method, we couldn't even identify what network architecture they used. So there was definitely a problem. So in summary, we really found that method descriptions were insufficient. So we had to take many assumptions, and I think if the code is not available, many of you would probably have faced the same situation. Perhaps you already had this. We also found that complex design choices were described less accurately. So something like model selection, although these are the things where we need the details. And based on what we found, we would give you the advice to focus more on reasoning for complexity, hyperparameters, and model selection, and also justification. So this is something that we currently don't have in Monai because it's not implementation specific, but these are advices and recommendations that we give. And as I said, I would really recommend checking out these Equator Network with the different guidelines for reporting. So related to reporting, the next topic I would like to touch upon are rankings. Something that is perhaps not all thought as having such a big impact, but rankings actually determine who is the best in benchmarking or in a competition. So imagine we have, for example, a segmentation task. You have multiple algorithms, you have multiple images. For each of the images, you have one or multiple metric scores. How do you determine the ranking? So I could, for example, for every algorithm, I could aggregate the results over the images. So for example, I use the mean or the median. But I could also, for each image, create a ranking of these algorithms and then aggregate over these ranks. Or I could be advanced. I could do some pairwise statistical testing and see how often is an algorithm significantly superior to others. So there are multiple choices, and the thing that we're often thinking is it doesn't really matter if I use mean or median, or if I do it this way or the other direction. It doesn't really matter. So the winner should stay stable, right? But that's actually not the case. And this is something we should think about, because the choices for the rankings make a difference. So we did an analysis of ranking robustness, and it took us a long time. So the data is maybe a bit outdated now with MiCA 2015 segmentation challenges, but all of the organizers provided the data. And so it took some time to get that data, but still, I think the results can definitely be transferred. And from what we saw in further research, it didn't really change over time. So we found that challenge rankings are very sensitive to a range of different design parameters. One thing is perhaps the most obvious: which metric did you use? This has a large impact on rankings, but also sometimes variance of metrics. So do you use Hausdorff distance or the 95% percentile? Or do you use NSD with this threshold or another threshold? So it makes a difference. How do you aggregate mean versus median, or this order or the other order makes a difference. And also who annotated the data made a difference in the rankings. So to give you an example, this is data from a real challenge with a ranking one we aggregated with a mean. If we exchange mean by median, the winner drops directly to rank 5. Going a step further, we calculated 12 different ranking schemes. And if we have a look at what happens, the ranking really changes completely depending on what we change. So for example, algorithm 1, the winner, dropped suddenly from rank 1 to rank 11 for ranking scheme 4, where I think we changed a metric variant. Someone from the middle is now at the top. The bottom algorithms are also quite good. So we cannot really trust such a ranking because results can be completely different. And what we advise is something actually very simple: visualize your results. So often we face the problem that we have page limits in publications, but I think this is something that we should focus on, visualizing your results. So we see an example here. So we have the case where we have 5 different algorithms that we're comparing, and we have the metric values here. So we have a box plot with the individual metric scores per algorithm on top here. And for the first example, we see directly from looking at this plot, I can directly see the ranking. It's very clear. And for the bottom example, it's very unclear because all of these algorithms are somehow in the same range, and I cannot directly say which one is better in total. However, both of these would yield the exact same ranking table. Why is this a problem? Well, in many publications, we don't have the visualization. We only have the ranking tables. So typically, we often also have like a mean estimate, but it's only a point estimate. So we don't get any intuition of variability, of confidence, of how close algorithms are together. So just having these simple plots already help a lot in terms of interpretation. And we can even go a step further. Let me briefly summarize the concept of bootstrapping in the context of ranking uncertainty. So bootstrapping is a statistical method if you want to basically simulate new data, if you want to see what happens to your data if you have small perturbations. So a standard choice would, for example, be creating 1,000 bootstrap data sets. So on the basis of your original data, you do sampling with replacement. So this may end up in a data set where you have specific data points multiple times and some other data points don't show up at all. And if you repeat this process 1,000 times, you get many, many different data sets with small changes compared to the original one. And based on, for each of these bootstrap data sets, we generate the ranking again. And then we can see how the ranking changes. And doing this like 1,000 or 10,000 times gives us an estimate of the variability and the uncertainty. And these results could also, again, be visualized. We call this blob plots because we have these blobs here. And the size of the blob indicates how often my algorithm achieves a specific rank across these bootstraps. So this big blob here indicates, okay, algorithm 1 is always on rank 1. Algorithm 2 is always on rank 2. So very clear ranking. In this case, no matter what I do to my data, I will always get the same ranking. On the bottom, we see this for the unclear example, where every algorithm achieves every ranking at some point. So very unclear ranking. And this would probably be a situation in a challenge where you would say, well, we don't have a definite winner. Perhaps we have a group of winners that share the best methods. And these and other methods are implemented in a toolkit. And I know that people are mad at us that we started this in R. I'm very sorry for this. We started this together with statisticians and they like R. However, it's still a very good tool. And we also have an online toolkit, which I will show in a second. So you plug in your metric values as a CSV file, and you get a full PDF report with many, many different types of visualizations and interpretations for analyzing your benchmarking results. And as a teaser, we have it on our to-do list to implement this in Python and to integrate it in Monai. So just give us some more time. But for the toolkits, so if you scan the QR code, you will get there. We have put all of this together. So you're a little bit less flexible than directly using the library, but still you can do lots of things. So here you see the example, you upload your data, you do some configurations. You can choose different ranking schemes and you're given some explanations on what is the difference between those ranking schemes. If you have decided on something, you can choose ranking scheme specific parameters like you use mean or median. You can decide if you do bootstrapping, how oftentimes do you bootstrap. And if you have configured all of these, you can then generate the PDF report. So you put all of this together. You wait a little bit, depending on the size of your data. This will take some time probably. And then you can download the report and you have everything together. So you have all of these different types of plots. You get explanations. So it's very nice to use actually. So I would recommend using this for your own studies. So when using rankings, I already said that the choice of metrics have a very high influence on the rankings. So let's talk about metrics next. So I have talked about metrics in previous Monai days, so I won't go into too much detail here, but if you're interested, there are previous recordings here, and I will focus a little bit afterwards in the next steps here. But let's have a look at an example first. So brain tumor segmentation is something that most of us do and like to look at. And here we see an example of a quite good prediction. So if we compare these two, reference and prediction, and also calculate a dice coefficient, which is the most commonly used metric in segmentation, we see that we have a 94% score on the voxel level, so a very good score. So we would assume that this algorithm is actually nearly as good as the domain experts. However, this is an MRI scan, so if we look at the different slides, we see that our algorithms are not as good as we thought because they are systematically missing small or tiny lesions. And this is something that the DICE metric is systematically overlooking because this metric is only looking at pixel or voxel level comparisons. So direct comparison, and they don't really care about a few pixels that we missed in a tiny lesion. So this metric is very misleading. And something like percentage of missed lesion would, from a clinical perspective, be very important and much more useful because for the clinicians, the tiny lesions are much more interesting than the large tumors. And generally, the question of which metric should I use is not trivial because there are so many different metrics out there, all of them designed for a specific purpose. How should you decide which metric is the best for your problem without having read all of those papers? So what we often do is, and these are basically replies from challenge organizers, is choosing a metric for their popularity. So as you see here, it's a widely used metric, it's commonly used, it's the standard metric. So we tend to do what others are doing but this is not always the best choice. We should think a little bit more on how we choose metric, although this is definitely not straightforward. So if we think of the most commonly used metric for classification, which would be accuracy, this comes with a very prominent pitfall. So if we have class imbalance, this metric fails. And to show an example, let's say we have a binary classification. We want to classify if a patient is sick or healthy. We have this very imbalanced data set here. We train our model and we get an accuracy of 97%, so a great score. However, this metric will not tell us that our algorithm is always saying that the patient is healthy, so yeah, not being very helpful in clinical practice, of course. And if we have used a different metric, for example, balanced accuracy, as the name says, it's balanced, so it's more fitting for a class imbalance setting, this would be much more suitable for the problem and would say, okay, 50% performance, this is definitely not a great algorithm. However, balanced accuracy has its own pitfalls. For example, it totally neglects predictive values. So we see a confusion matrix here where we have lots of negative cases. So we see, okay, we have a very high number of true negatives, which is great, but still, nearly 5,000 false positives is a very high number. And if we think of like a screening scenario, so many false positives, just think of it from a clinical perspective. However, our algorithms do not really care about false positives, and they still provide very good scores. So we should, for example, use something like positive predictive value or Matthew's correlation coefficient. However, those metrics, again, have their own pitfalls. Matthew's correlation coefficient, for example, is dependent on prevalences, which makes it a little bit harder to compare across different data sets. It is neglecting class importance, and it's hard to interpret. So basically, if you follow this guideline, this path, you won't find the perfect metric. Every metric has problems, and if you're interested in that, I recommend checking out these two publications here where we summarize them. And feel free to challenge us if we missed something. Feel free to contact us, and we're always happy to include more in the dynamic preprint here and also include you as the co-author. But it's always better to solve these problems, and perhaps you know the Metrics Reloaded effort where we work together with many experts from different domains working on problem-specific metric recommendations. And if we stick with this classification example, this is the example of one of the decision trees that we have here, where we ask different questions related to metric selection that are important based on all the pitfalls that we have found earlier. So for example, is there an unequal interest across classes? So is one class more important than the other? Or are there specific costs or weights for class confusion? So is a false positive or a false negative, one of them is more severe for our problem? Or do we have class imbalances? So we ask all of these questions and make sure that you're not using the metrics that have those pitfalls. For a situation where it's a little bit up to the user and we couldn't basically integrate every single potential tiny use case, we also provide decision guides that help you with your decision. So based on your previous responses, we collected the basically remaining pros and cons of these metrics so that you can decide on your own what are the things that I can live with. For example, Matthew's correlation coefficient, as I said, is not so easy to interpret. Perhaps you don't care. Then, okay, use that metric. That's totally fine. And basically what we are recommending is using multiple metrics. So that's an important general recommendations, because every metric has pitfalls, and using multiple metrics will give you a comprehensive overview of your problem and of your validation, and also may compensate pitfalls from the other metrics. So for example, for classification, we can select different kind of counter metrics that rely on the confusion metrics. You can select curve-based metrics, calibration metrics, something that is very specific for your problem. So you have the choice of multiple metrics here, or non-reference based metrics. Without going into too much detail, our general approach is here, you start from your research question. And then you break it down into different problem properties. So we ask questions: do you have class imbalance? Do you have costs for class contributions, and so on? And basically we call this a fingerprint, and you have these different properties where in most cases you say just yes or no. And based on these, we can recommend the metrics that are really suitable for your problem. And if you look at this as a whole, you see it looks a little bit complex, but what we saw earlier is this blue path here for classification. We also include recommendations for object detection and segmentation. And this was the first part, so the theoretical the theoretical work, and then we found, okay, it's quite complex. We need to make this a little bit more easy to use for people. So on the one hand, we have asked the community, what are the use cases for which you would like to see recommendations? So we collected them. Here you see a few of them. We have more in the appendix of the paper. We sat together, worked on the different properties, and here you have the recommendations. Something else which I also found, to be honest, quite annoying, when I was looking for the details of the different metrics, it was so hard to find all the information for one metric, because every paper only focuses on one specific aspect. So we thought, okay, we need cheat sheets for the metrics where you find the important information for one metric in one place. So the formula, description, multi-class definitions. Is this metric dependent on prevalence? Do we have specific important relations? What are pitfalls? And so on and so forth. So these are things that you also find in the appendix of the paper, which really help if you want to know more about this. But I guess the most important for today here is that we implemented all of these metrics within Monai. Because one of the pitfalls that we found is, depending on which library you use, which implementation you use, you will get different results. This is, of course, annoying and not what we want. So we worked on standard implementations, and here big thanks to Carol, who did most of the work. So we have this metrics reloaded, which is not directly integrated into Monai, but it's part of the framework. So, but you can also use it when you're not familiar with Monai. So that's basically the whole thought behind it. So you can use it with or without, and you find all of these metrics that we have in our current work. And also, if this is all too complicated for you and you don't really care about theory, we have put together an online toolkit again, where basically you don't have to think about the theory. You're guided through the whole process, similar to the rankings thing. So you choose your problem category, and you're giving, you basically generate everything on the fly. So you're answering different questions, you get some explanations, some visualizations of what we mean by this. And when you do this throughout time for your very specific problem, the framework will then give you the specific recommendation. So you really don't have to worry about everything. We recently worked on a new version where you get a full report at the end, and also are linked to the different cheat sheets of the metrics. So this is something that I would also recommend checking out in the future. The question is based on what we have done so far. So you see, for example, for metrics reloaded, we only have classification, detection, and segmentation in there. So an obvious step would now be to extend metrics reloaded to other fields. One of the things that we're currently working on, so this is work in progress, we don't have full results yet, but is extending metrics reloaded for videos. So our main focus here is surgery, but I'm pretty sure once we're done, this also applies for other video data, like, for example, video ultrasound or longitudinal data, perhaps also. We need to see, but we're still in the progress. The main idea is that typically in video analysis, what we currently do is we're aggregating frame-based metrics. So basically, we do that frame by frame, and then we put everything together without thinking of this temporal resolution. So what we're recommending is actually using metrics for video analysis and thinking of all those problems that can be there when we're aggregating incorrectly. So this is the current scope, surgical video understanding with things like tool detection, face recognition, or scene segmentation. However, as I said, I think this probably also relates to other video-based problems. So currently we're in the process of collecting pitfalls. So we will follow a similar approach how we did this for Metrics Reloaded. So one example pitfall here would be that we have different surgical phases if we do a full surgery. And not all of these phases are really relevant. Some of them are more complex than others. And probably we're not really interested in those phases when nothing happens, where you don't really move your instruments, where the surgeon is just talking to someone. So we're more interested in the relevant phases. But what we do, as I said, we typically just put all frames of a video into one pot, and we just, for example, calculate the mean dice for such a segmentation task. If we would now look at the results per phase, we would see that for the more complex phases, the relevant ones, the scores are much lower. And if we would only look at those, we have a mean dice of 64% versus 87%. Also, we're currently looking into different aggregation schemes. So for example, only doing it for a specific phase, or do a weighted phase aggregation, or do it video-wise, do it phase-wise, do it frame-wise. And we see that a ranking, also this is based on a real challenge, changes a lot depending on how we do that. So this is the one thing that we're currently working at. The other thing that we started is Metrics Reloaded for reconstruction and synthesis. And I think this is a very relevant topic also now if we think of all these generative AI models, foundation models. I think this will become more and more important. So we have here we see an example pitfall now from photoacoustic imaging, but this applies basically to also to MRI and to other modalities. We often have the problem that a large proportion of the image is background. In the validation, we typically don't really think about this, so we're calculating our metrics over the entire image. But what we should do is do it only for the foreground, so the things that we're really interested in. And as you see here, there's a large difference in scores. And also one thing that is, again, very relevant also for MONAI, there are many, many different definitions of the very same metric. So for example, if we look at signal to noise ratio, here in the study, they found 15 different definitions on how this metric should be defined. And you can imagine thinking of libraries, every library will choose a different definition. So of course you will get different results. So also long-term goal here would be to talk about the different, think about what is the most accurate definition of a metric and which one should be implemented. So it's definitely planned that we extend the current implementations. And now the QR code just vanished. I'm sorry for that. So if you're interested in joining this initiative, please feel free to reach out to me. We're currently looking for more experts on this. And what I wanted to show here, but it's gone, would be a QR code for a survey where we're collecting pitfalls. So please feel free to reach out to me and I will send you the link to that poll if you're interested in joining the initiative. And the last thing that I would like to talk about is related also, and also something that we plan to integrate into MONAI, related to the question, is method A really better than method B? I already talked about the problem that we often only see these results tables in papers, right? So we often have the tables without the visualization. And often the proposed method is highlighted in boldface to show our results are the best and we're outperforming the others. And the problem is, which was also found by the FDA, is that statistical analysis plays a crucial role when we assess machine learning. However, it's often underappreciated. And there are still many publications that only have these point estimates without any quantification of uncertainties. And this is what we looked at in our current work and what we're extending right now. We wanted to know what is common practice with respect to variability in medical image analysis. And related to this, we have some further research questions. But let me start now with the first one, so common practice. What did we do? We analyzed all MICAI 2023 segmentation papers, so a little bit more than 200 papers. So And what we found, variability reporting is very poor, so similar what we saw with challenge reporting. More than 50% of the papers didn't report any kind of variability. We found only a single paper that reported a confidence interval. And for those few that did report some kind of variability, for most of them, it was actually unclear what it was. So it was not specified, for example, if it was a standard deviation or a standard error, or if it was a standard deviation, how that was computed. So we definitely have a problem here. And given the fact that there were so many papers where we didn't have variability, we wanted to know if we can somehow recover that variability from the available data, especially if we think of confidence intervals. This is something that, as I said, we found only a single paper here that reported standard deviation, confidence intervals, and it's a very important parameter because standard deviation gives you an overview of the variability depending on your data. The confidence interval gives you an estimate of how confident am I with my point estimate. And ideally, you would have a narrow confidence interval, so something like this. The wide confidence intervals basically said you were not very confident with your point estimate, and yeah, it could lie also on the bottom side here. So what did we do? Very briefly, we used the data from the medical segmentation decathlon, where we also had access to basically the results of the participants. And we found that there's actually a correlation, or I wouldn't call it correlation, but a dependency between the mean dice and the standard deviation. And you could actually draw something like a polynomial curve on these values to approximate standard deviation. And we didn't want like a perfect approximation or a formula, but just to give us some kind of intuition of the variability of the data. And we used some external data to see that actually this approximation was valid for a meaningful test set size. So for very small data test set sizes, it was not working so well, but for data with more than 20 cases, it was a reasonable approximation. And we used this to approximate confidence intervals. So if we just ask a question, by which margin do you think does the proposed Mikhail method beat the second best method? So what is the delta in dice between the first method and the competitor, basically? So we found a median improvement in dice of 0.01, which is not that much. And ideally, the width of the confidence intervals should be smaller than this improvement to be meaningful. However, we found that in reality, the median confidence interval width was 3 times larger. So we're not very confident with this. And actually, we also found that in many cases, the mean performance of rank 2 was within the confidence interval of rank 1. So there's a very high chance of both of them flipping, so that this claim of outperformance is in many cases not valid. And what we're currently doing is we're working on deriving something like the probability of rank flips for those papers. And we also plan to extend this towards MONAI, so that you directly have the confidence intervals that you can report in your papers, which will give you some more insights in your results. Yeah, and with this, I would like to end here, reminding you of the importance of validation. So I hope I made my point, showing that we should go the road in this direction towards the real goal. There are many things that we need to consider when it comes to validation. It's not easy. So the working group is trying to help you, to give you some advice, to give you guidelines, to give you implementations. And I hope that we in the future try to always optimize for the real goal and not go into the wrong direction. And with this, I'm very happy to answer any questions, and thanks a lot for your attention.